let's talk about one last property of Brownian motion. Okay, basic. There are many different. One last property that the Brownian motion is Markov process. It's a Markov process. So, definition of a Markov process. And start with the defining Markov process. So, in both cases, discrete time and in this time as well, we say that x of t, time domain, is the Markov process if for all bounded well sets. Another thing I like it. Okay. Let me begin by defining what we mean by Markov process. We're going to say that a process is Markov. So if you take any bounded Borel mass F, from R to R, we have the expectation that x expected value of x of t given if you know about everything about the process about the process up to the time if equal to the expectation is equal to expectation of t given sigma is generated by x. Okay. You have this strange definition of the process. So, does it meet with our previous understanding? I mean, if you think about it, what does this say is that imagine you are interested in computing the expectation of, maybe I should say explicitly, that 0 s and p is s is between 0 and time t actually. So imagine you want to compute the expectation of f of some function at some future time t, and you know everything about this process from the time 0 up to the time s. In other words, you have a sigma number that is generated by the process, but from 0 up to the time s. So its entire history up to the time s. This is same as that you compute the expectation of xt given the sigma free generated by only x s. Okay, the s is the current instance. S is like the current instance. Okay, so the expected future, given that you know past and present is equal to the expected future given you know the present future. So it's a kind of a memoryless process. Okay, it's a kind of memoryless process actually. Because the future depends on only on the current instant. Actually, the current instant in this case. That's right. Now, what we can prove, so let me quick remark. Quick remark. quick remark is this, that this condition is Markov property of the problem with star is equivalent. Okay? Equivalent to the same property, okay, when you take f in the indicator function of a Borel set actually. E is the Borel set for the entire time. P, in other words, probability that x of f and x of t will stay in the Borel set. Think about it, if you take an indicator function of a Borel set here, what does that is going to mean? This is going to mean, in other words, the indicator function evaluated at x2. So this is going to mean that the probability that xt is in this Borel set, given everything about the process, okay, up to the time s, okay, up to the time s, same as the probability, because expectation of an indicator function is, you can write it in the terms of probability that same as x of t is in the Borel set, given that the density of being calculated by x of s. So this would be an equivalent condition. Okay. Why this would be equivalent condition? Just give you a heuristic argument. Obviously, from this, it is easy to deduce this. Just take f to be indicator function. Okay. How about other way around? What do you think? So you can start with, for example, if you want to show that if this is true, why this must be true. Okay. You can start with, for example, a non-negative function. Okay. A non-negative function, measurable function. Okay. And then I know that for this non-negative function, I can find a sequence of the step functions. Okay. In other words, sequence of indicator functions that would approximate that. Okay. And that sequence of indicator function that will approximate f by monotone, not monotone, but dominated convergence theorem, the integral of that sequence of indicator function will converge to the integral of f. Okay. And obviously, if you have some, a generic function, for example, flex value that, then I can write this into the positive and negative part. So argument will still do that. That's an equivalent condition. What I would like to show that Brownian motion is also a memoryless processor. So its future trajectories, does not depends on how it behaved previously. It depends on the
space on.
You have a state space, but that is continuous time. Therefore, I'm defining it for the continuous time first. But if you have discrete time, yes, you will have some state space like that. Okay. So I'll prove a generic result, which is, it's not only true for, for Brownian motion, but any process. So if you have a process, good process, okay, I'll write this assumption. If it has independent increments, it must be always Markov. That's what. If it has independent increment, it must be Markov. So I know Brownian motion has independent increments, so it must be Markov. But the result is much more general. That would be the example. This is what I would like to show. So I would like to begin with an observation. I would like to motivate, for example, let's start with, okay, so what would be the same definition but in discrete time? So you're going to say expectation of f xn plus 1 given sigma generated by 0 to n is same as expectation of xn plus 1 given sigma x and y etc. Okay. So let me return to random walk. Return random. So let's see that random walk is the Markov process. It's a Markov. So should be Markov process, but does it satisfy this definition? So I know that if I would like to write, my earnings, so Zn could be understood as the cumulative gains you have, after, for example, n plus 1 gains. Then I know that this would be same as the cumulative gains after n gains plus the outcome of the n plus 1 gain. And we know the outcome of n plus 1 gain can be 1 with the probability E r minus 1 with the 1 probability r minus b, and 1 and minus 1 are not necessarily equal to hn minus hn. Anything you like. You make it? So what would be the expectation, for example, it starts with a very simple thing, Zn plus 1 given sigma field that is generated by Z naught up to Zn. Okay. Then this would be same as Zn plus L n plus 1 given sigma field generated by Z naught to Z. Right. So what would be the conditional expectation of Zn? So it's measurable here. So taking out what is known from it tells you that this is Zn. And Ln plus 1 is independent of all of these arguments. Right? So this must be Ln plus 1. Okay, expectation. Yes. Expectation of Ln plus 1 which is 0. Sure. Okay. How about the other side? So if I have the same Zn plus 1, and this time I would like to just see from the perspective of Zn. So still you have the same result actually, that this would be
written as
this would be Zn plus 0. This also would be Zn plus 0 precisely for the same result. We can say that this process really is a good process actually. Are we happy with this proof?
yes.
Now, instead of, for example, Zn plus 1, if I take, for example, expectation of a bounded Borel function. Okay, so imagine you have a bounded Borel function that is the base value from R to R, and you want to compute the expectation of f of Zn plus 1 given sigma field generated by Z naught up to Zn. So instead of, so you can treat that as a particular instrument of it, just take the identity function and you get this. So what this would be, so I can say that this is same as f of Zn plus n plus 1 given sigma of Z naught to Z naught to Zn. Now, can I write this as, so think about it. I don't know how does f looks like actually, but I know that it depends on Zn, that is measurable here. So if it involves some expression involving Zn, so it will stay stable, and this guy is independent. So I can also treat this as that this is same as the expectation of f of, let me define a function for example. Let me define a function capital F, and then capital F goes like that. So it's f of xy, okay, and I'm defining it to be the sum of x plus y. Okay. Then I can see this guy as expectation of f of Zn and Ln plus 1 given sigma field generated by Z0 to Zn. Okay. Now if I see this function, now this is measurable here. If I fix this, for example, and see this function as a function of Ln plus 1, what can I say about it? So it must be independent. So in other words, I can say that this would be, for example, g of Zn. Okay. Now what is g? Where g of x is the expectation of f of x. X is fixed.
Say,
And
L
L
plus
is 1.
say,
Okay. So there's expectation of such a function will be this. Now I like to come to the other side again and I look on the other side. That's what I'm pretty much sure you're gonna get precisely the same thing. So instead of taking say f of Zn plus 1, given the sigma field generated by Zn should be same as the equation of f of say Zn plus 1, Zn plus Ln plus 1, given sigma field generated by Zn. And I can also see it again as the left of Zn, Ln plus 1 given Zn. Okay. This should be same as 1. If I fix this, this must be not 0, but it should be same as independent of this. So this would be again g of Zn. Okay? Again g of Zn. So you have equality. So this shows that this random walk explicitly satisfies the definition of the Markov process. Okay? Why I went through this example? Because I would like to write an abstract result, which is pretty much analog for it. Okay, this example. And if you want to see the proof of it, you may go back to this probability for finance book by Kapensky and just see the chapter on the condition expectation, which is there. So let me state the result, which I will use letters. So imagine I have a sigma field, graph G, be sub-sigma field. It's a sub-sigma field of a sigma field F. Okay. Now, if X is G measurable, if X is G measurable, and Y is independent of G, okay. Y is independent of G, then for any bounded model F from R to R, okay. We have what? The same, the expectation of
S from both.
okay, so this is not just F, it's capital F. Okay. Capital F, that is an F from R2 to R. Is that expectation?
F of X from R.
That's why given
G.
G is same as G of S, where the G is is same as that. So let's take function G.
Sir, कुछ भी हो सकता है.
Yes.
Consistence.
G of x should be, so we define it as that to evaluate it at x compared to y. So it's really abstract version of what we did. So we can do this a lot. So you can see it from the finance and the chapter of conditional application.
Sir, phase y preference.
X को कर लेना. X को. Okay. Y is independent of G. Then so if the best way to say would be that if you know that Y is independent of G and you are computing the expectation of f of x, this Y is not going to add anything into the expectation. This would be same as G of x. So why I want to do this now? Why do you do this? Because I want to write a proposition. Use it. Proposition goes like this. So if you have any process, stochastic, discrete, continuous, any process with independent elements. Independent elements is Markov. Okay, with respect to natural filtration. Natural filtration defined by obtained food. Such with respect to its natural filtration. Okay? Not in general, but yes, with respect to structure. So we have any process that has independent increments, it must be Markov. Okay. If this is true, I know Brownian motion is independent increments. Okay. In fact, learn processes which are kind of very generalized notion actually has independent increments.
Scale random. Scale random.
Everything. Okay? You just make sure that it has independent. Argument would be very much like this. Okay? Something else. So imagine I want to compute f of x of t with the same notation, given the sigma field generated by x of r, where r is everything from 0 plus. Okay. So what should I do with it? Do something like this. I have to exploit the independence of it.
It's to
Add subtract the next. Add subtract if I x of t, add, for example, x of s and plus x of is given here. Now this bit is independent here. Because this is a sigma field generated by everything up to this. trying to explain you that why it must be independent. Because increments are independent, so x of t minus x of s is independent of increments, say x of s minus x of 0, right? Then it would also be independent of the sigma field generated by that process. Okay. So basic problems. Which one? Okay, so obviously we are trying to follow the definition, so we are assuming that 0 is somewhere here, s is here, and t is here, right? So we said this increment process has increment here, but this is independent of it. Then this will be not only independent of it, but independent of increment here. It will be independent of all, sigma fields that are generated by increments of the
We have an interval 0 less than r and r less than s. Then there should be 0 less than s and s should be less than t.
And he has to help by default. That's it. So हम ये कहते हैं, I want to predict something about this part, and I know all this. So I'm going to say this doesn't add, because this doesn't add anything into your portfolio, because process has independent entity. This is my assumption. This increment of the process over this interval is independent of the increment of the process this way. So if I even generate a sigma field out of this increment, it is still not dependent. This here will be independent of this. I can do the same actually. So this would be same as expectation of I can say this would be same as g of x of s. G of x of s with the same notation. Where the g of x is what? Is expected value of f of x and this increment. So we are fixing the second argument of the first. This is something that we should. Now this x is arbitrary value. This is the fixed. And a same kind of argument would be true for the other side as well. Okay? So you will see that if you cast out all of the information, because to compute this probability, I don't need everything here. So I only need, the information. Okay. Can you see if I go the way it look like? So let's say I have expectation of f of xt given this time sigma field was generated by only x of s. Okay. And we'll see that it will reach to the same conclusion that we have of x of s and x of t minus x of s. ठीक है? By why x of t minus x of s should be independent of it? Because you can treat this x of s as x of s minus 0. Like this. It shows that any process, whether the dimension increments must be one, should be memoryless. Okay? So it's the case with the Brownian motion.
Expectation of x minus positive.
X of t minus x of s.
We were constantly x involved or x must be. I'm
saying I have a function the kind of a function that depends on itself. Okay. It also depends on this, but this is a fix for the entire value of x. No matter what value x you take, this would be, so this increment would be fixed. Okay, so I'm not changing this. So in other words, it's like you are saying that if I have a function f of x y equal to